The last topic I want to introduce in the context of fluid dynamics has to do with the concept of vorticity, which is a technical word for what we already know in terms of eddies or whirlpools or something like that, but you do not necessarily have to have whirlpools or eddies in order to have vorticity in a fluid, as we will see. I need to introduce a little bit of vector calculus to do this, but we will do this in slow steps. You already have seen that if you give me a scalar field phi of r and t, so that is a scalar field. Well, let us forget about the time dependence for the moment. If you give me a scalar function of the position coordinates, then from here we can form a vector field, namely the gradient of phi. Or the directional derivative of the scalar field, and that is called the gradient of phi, written as grad phi or del phi in this form. We have also seen that if you give me a vector field, let us say some u of r for instance, from here we can form a scalar field which is the divergence del dot u, and that is the divergence of this vector field here. It gives you physically, it is equal to the flux per unit volume in the limit in which this volume goes to 0 at any given point r. And we have a formula for it which is written by writing these out, for instance in Cartesian or any other coordinate system. We can write down what sort of derivatives with respect to the position coordinates this involves here. For instance in Cartesian coordinates it is delta ux over delta x plus delta uy over delta y plus delta uz over delta z. But in other coordinate systems it gets a little more intricate, we will not go into that right now. The question you can ask now is, from a vector field can you form another vector field, and the answer is yes. So here is a vector field u of r, and from here you can form another vector field which is called the curl of this field, and formally, operationally, although that is not the basic definition, operationally just as this is del dot u, this other field is given by del cross u, and I will write down this explicitly in a moment here. Physically what it does is the following: if these are the lines of the vector field u of r, then at any point, say here, you take an infinitesimal area element delta A pointing along some unit vector n. While an area itself, if it is a curved surface for example, you cannot associate a unique vector with it, an area element is essentially a planar object and you can associate a unit normal with it. So if this is the direction of this normal n to this area element delta A, then what you construct is the so called circulation of this vector field by taking u dot dl along a closed path around the periphery of this area in this fashion. This quantity is called the circulation of the vector field, and dl is a line element which changes direction as you move along here. Each dl is infinitesimal, a small tiny vector, and you move along here, it changes direction, you dot it with the u at that point, and this is called the circulation of the vector field u around this circle here, this contour here C. This is the circulation. You find the circulation per unit area and you take the limit as delta A goes to 0. The limit is finite, just as we took the flux per unit volume over an infinitesimal volume element and the surface area delta S of that of the volume element went to 0. In the same way, this periphery, the circumference also goes to 0, the area goes to 0 in such a way that this quantity, if it has a finite limit, it is called the curl of this vector field. So this is the definition, it is called the curl of u at the point r. So, this is the point r in some coordinate system, and the curl of u is defined as the circulation, this is the circulation of the vector field. So, the circulation per unit area is the normal component, it is the component of this vector along the direction n. Or if you dot this quantity, okay, so let us leave it like this. So, to find the curl, full curl, you are going to have to take different, say, area elements pointing in different directions, and in each case you find the normal component by computing the circulation per unit area. Now, this is a cumbersome thing to do, so the obvious thing to do is to take a convenient contour and find out what it is in Cartesian coordinates. For example, it turns out that curl u in Cartesian components is equal to Ex times delta u z minus delta u y over delta z plus E y delta u over delta z x minus delta u z by delta x plus E z delta over delta x u y minus delta u x over delta y. So, that is the formula for the curl, and it is clear that this quantity can also symbolically, it is exactly the same as writing del cross u. So, I emphasize again, although it is del cross u and del dot u for the curl and divergence respectively, these are not the definitions of the divergence and curl of a vector field. The definitions are, in this case, the flux per unit volume and the limit of the flux per unit volume as the volume element goes to 0, and this is the circulation per unit area, gives you depending on the normal to the element of area, it gives you the corresponding component along that direction of the curl of this vector field. And this is, if you like, an algorithm for computing what the curl is once you tell me this vector in Cartesian coordinates. Now, the question is, what is the physical meaning of the curl of the vector field? But before that, let me see where this, let me write down where this comes in our problem of the fluid flow. Recall that our equation of motion of a fluid element was this plus v dot del v, this thing here was equal to, on the right hand side we had minus the gradient, and let us look at barotropic flow as usual, dp over rho of p plus phi plus f viscous, which I am dropping all the time here. This quantity, when we took the dot product with v, we discovered it was essentially the gradient of half v squared. But now, without taking the dot product, we can simplify this alone, and it turns out that this can also be written as this minus v cross the curl of v. So, that is del cross v, this form, that is equal to minus the gradient of integral dp over rho of p plus phi plus 1/2 v squared. So, the statement is v dot del on v is the gradient of half v squared, which I bring it to this side, minus v cross the curl of v itself, and this quantity del cross v equal to the curl of v equal to some chi, which is of course a function of r and t in general for a fluid. This quantity here, this chi, is called the vorticity. You can define a vorticity at every point in space at every given time for a velocity field. If this is a function of r and t, so is this a function of r and t in general. And in terms of this vorticity vector, this quantity, this thing here becomes delta v over delta t minus v cross chi equal to this quantity on the right hand side. That is the general equation to a fluid element. So, let us write that down also. Now before I say what happens to this quantity in general when you have fluid flow which has got vorticity of this kind, before I do that let me also point out another remarkable statement, which is the following. We need to geometrically interpret this vorticity here, and the simplest way of doing this is as follows. It represents, chi represents twice the local angular velocity of a fluid element if you regard it as a rigid body. And what does this mean? It means that if you have a flow and you focus on some fluid element, you are on that fluid element, you ask, never mind how the fluid is flowing around it, you ask, does this fluid element rotate around itself or not? If it does, then there is a chi or there is a vorticity, and if it does not, there is no vorticity. And let us immediately give an example to show you how this works. So let us look at a flow along a horizontal canal, and for simplicity I will look at the surface flow, we will not look at the depth of it. The depth is along the z direction say, and the flow is the surface of the canal is in the xy plane. So it looks like this. That is the x direction, this is the y direction, and let us put our coordinate axis so that down the middle of this canal is the x axis here. And the flow is streamlined, all the flow lines are parallel to the banks of the canal on both sides. And let us suppose there is viscosity in the problem. We have already seen this when we first did dimensional analysis for Poiseuille flow in a pipe. I pointed out that if you have a horizontal pipe, the flow is maximum, the velocity is maximum at the center or axis of the pipe, and it tapers to 0 at the two ends because of viscosity. So if I were to draw the velocity vector symbolically, you can see that the vector is going to be fairly large here, and then it is going to be a little smaller here, it is going to be even smaller here, even smaller here, and so on till it is essentially 0 at this point and this point. And let us give this some coordinates. Let us this is the line y equal to 0, this is y equal to a, and y equal to minus a. So the width of the canal is 2a, and this is what the flow, the velocity vector looks like at these points, and of course at this point it is exactly the same in this form, etc. So these are small vectors, these are medium vectors, these are small vectors, this is even tinier vectors, and so on. So to simplify the picture so that it does not complicate it, let us erase all these arrows. And you have a parabolic profile of this kind in which the maximum speed occurs in the center and it tapers off in this direction on both sides. Now what does the velocity field look like in this problem? It is immediately clear that V at any point, we are only looking at the surface, we are not worried about the z coordinate at all. V at any point is the speed multiplied by Ex, because it is along the x direction at every point, and the speed is dependent on how far you are away from the center along the x axis. The further up you go, the further up or down you go in the y direction, the speed decreases. So this V is a function of y alone, and it has got an x component of the velocity which is dependent on y, and therefore you can see that the curl is not going to be 0 in this problem. And what does this, how does this manifest itself? Well, I have not proved this, but we can show that V of y equal to some constant times a squared minus y squared in this problem. It is symmetric about y to minus y, that is clear. It must be 0 at y equal to a and y equal to minus a, which is the banks of the canal, and in between it is largest. So the function is quadratic and one can show this fairly straightforwardly, and it looks like this. V of y looks in this fashion here, and this is of course Vx of y, and that is the only component of V that is not 0, because the flow is along the parallel to the x axis everywhere on the surface. Okay. Once you have this, the curl of V, the only component of the curl of V that is non-zero, if you recall the formula for the curl that we wrote down earlier, is Ez delta over delta x Vy minus delta Vx over delta y, and this component is 0 because the velocity has no component in the transverse y direction. So you have Ez minus delta Vx over delta y, but Vx of y is given by this. So this is equal to minus k, there is a minus sign here and a minus sign here, so this becomes k times 2 y. So I differentiate this with respect to y, I am going to get a minus 2y, and I kill the minus sign, and you get a 2ky times Ez. This is the curl of the velocity. So even though the streamlines are parallel lines, they are straight lines, you still have a curl, and the moment you have a velocity with a curl, the flow is said to be rotational if the curl is not identically 0. If the curl of a velocity field is identically 0, the flow is said to be irrotational. It's just a piece of terminology, but what it implies is the following. It implies that fluid elements here have a local angular velocity which is given by half this curl here, in other words proportional to ky, equal to ky times Ez. What it means is the following. If I put a small raft here in this fashion and it floats along, then because the velocity is larger here and smaller here, as time goes along this raft will rotate by about its center in this fashion, and the angular velocity of that rotation is what is measured by this curl here, according to this rule which says 2 omega equal to chi. So this example illustrates clearly what is meant by the curl of the velocity field. It gives you the local angular velocity apart from this factor of 2 here, and not surprisingly you can see that as you go down in this, as you go up here or go down here, the rotation rate changes, and that is what this is trying to tell you out here. Okay. Now where does that take us here? Well, now you can see that if the flow is steady, this equation delta V over delta t is 0 out here, and moreover if the flow is irrotational, then, well, this term is 0 and this term is 0, and now even without dotting with V, this whole thing has a gradient which is identically 0. That means along any direction whatsoever this scalar function cannot change. So it says that integral dp over rho of p plus phi plus half V squared equal to constant, the same constant throughout the fluid. So we have a powerful statement. It says that this combination here, this scalar combination, which represents some kind of energy as you can see per unit volume of the fluid, this combination does not change throughout the fluid. So, it is the same on all the streamlines. We already saw that rotational or irrotational flow, we do not care as long as it was steady, barotropic, etc., etc. We had Bernoulli's principle which told us that this combination was constant along each streamline. Now, if in addition there is no vorticity anywhere in the fluid, then this constant is the same on all the streamlines. So, it is constant throughout the fluid, this combination here. If the flow is rotational, then we have already seen that this quantity here is constant on a given streamline. So, here is a given streamline and it is constant along that, might have a different value on this or different streamlines, but again if the flow is irrotational, all these constants are exactly the same. Even otherwise, if I took this equation and it was steady flow, so that goes away, and I dotted this not with V but with chi. Now, if I dotted it with chi, then since chi dot V cross chi is identically 0, the scalar triple product is identically 0 because V cross chi locally is perpendicular to chi and this is the component along chi, so this dot product is 0. Since this is so, chi dot the gradient of this quantity in the brackets integral dp over f of over rho of p plus phi plus half V squared is equal to 0. And just as in the previous case where it was V dot this quantity which was 0, and I said therefore this quantity is the same along a streamline, a flow line of the velocity field V, a field line of the velocity field. Similarly now it says this quantity does not change, there is no gradient component along a line on which chi flows. In other words, the field lines of this vector chi, the circulation vector chi, the vorticity vector chi are such that this combination does not change along these vortex lines. So, the field lines of chi are called vortex lines, and integral dp over rho of p plus phi plus half V squared equal to constant along each vortex line. So, this quantity is constant not only along each streamline, but some given value along each streamline, it also has some given value along each vortex line. And then of course you could ask what happens if the vortex lines and the streamlines exhaust all possible directions in some specific sense. Well, then the whole thing is constant along the entire fluid. I mean, this is what happens if you took two cylinders, concentric cylinders, and you rotated the inner cylinder keeping this one fixed and you put fluid here, then the streamlines are lines which are concentric circles with this center as axis. There is no flow in the z direction at all, and then each vortex line, each streamline is a circle of some kind like this, and each vortex line is a line along the cylinder formed by these little rings here, these. And now you are told that this combination is constant along this line, it is also constant along this line, therefore it is constant along that line and so on, and therefore you have exactly the same value everywhere. So, there are these special kinds of flows where you can make very general statements based on these principles here of what happens to the vorticity or what happens to this quantity here, this conserved quantity along a streamline or along a vortex line. So, the fact that it remains constant both along streamlines and along vortex lines gives you a very powerful way of analyzing fluid flow. We have not talked at all about the other equation, the equation of continuity, but along with this statement you also have the statement that delta rho over delta t plus del dot rho times V equal to 0, and if the fluid is incompressible then this term goes out and that is a constant that goes out and you have del dot V is 0. So you are left with the smaller problem of analyzing a velocity field such that its divergence is identically 0 and its curl obeys certain simple equations which we can explicitly write down, and then a large number of formal theorems can be proved which are very useful in practice in fluid flow. So to summarize, in a nutshell we have seen the most basic elements of what happens when you took Newton's law and applied it to the motion of a fluid. The fluid is described by a density field and a velocity field at every point. You also have to specify the pressure field on it, namely what the pressure is at every point at every time. Then in cases like barotropic flow where the density is a function of the pressure alone, we can go a great deal of distance in analyzing this complicated partial differential equation even though it is nonlinear if you neglect the viscosity using these general principles. On the way we saw that concepts such as divergence or gradient or curl and so on of a vector field appear very naturally. The next step of course would be to put in the viscosity term and ask what happens when you have viscosity, when you add viscosity. I am not going to do that. You end up with an equation which improves upon the Euler equation that we have written down here. It is called the Navier-Stokes equation, and in principle it contains all the information you want along with the continuity equation to solve quote unquote in principle to solve the problem of fluid flow. But you must add to this boundary conditions, initial conditions and so on, and the mathematical problem of fluid flow is formidable, especially the problem of turbulence. But I hope this has given you some introduction to the basic ideas involved in analyzing these fluids and how the fundamental equation of fluid flow already follows from an extension of Newton's equation of motion. I think I will stop here.